All right, in this set of notes, we're going to start our discussion of inscribed angles, and in the next set of notes, we'll talk about inscribed polygons. So we start off with a couple of definitions up here at the top of the page. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. And we can see in this case that we have an angle whose vertex is on the circle and the sides of the angle are two chords. Remember, a chord is a segment that connects 2 points on the circle. An intercepted arc is the arc that lies in the interior of an inscribed angle and has endpoints on the angle. So in this case, we've mentioned that our inscribed angle is angle DEF. So this is angle DEF. Now, if I were to trace that angle, I'm going to trace it here in this same pink color. I know that E is its vertex, but in this case, we also know that points D and F are the other two endpoints of those two chords. If I consider the interior of that angle, remember that's the part inside the angle, then this arc lies inside the angle itself. This is what we refer to as the intercepted arc. And we can see in this case that this is an arc that happens to be visibly less than a half of a circle, less than a semicircle, less than 180 degrees. So if I were to name this particular arc, I would name it with 2 letters. So our intercepted arc in this case would be arc DF. And remember, when we name an arc, we use those 2 letters, and then we draw that little umbrella type arc over the top. So the intercepted arc lies inside, in the interior of that inscribed angle. And remember, this only applies to inscribed angles. It does not apply to central angles that we talked about before, where the vertex would be at the center. Only when the vertex is on the circle can we talk about the intercepted arc and the inscribed angle. Now, these next 2 theorems are going to be some relationships that exist with the measures of these inscribed angles and the intercepted arcs. So our first theorem, if an angle is inscribed in a circle, then its measure is half the measure of the intercepted arc. So I've gone ahead and drawn myself a circle here, and we are going to add to that an inscribed angle. I'm just going to use the word intercepted everywhere today, I think. All right, so I'm going to make an angle with a vertex on the circle, and I'm using a straight edge here. If you want to estimate it, you're welcome to. Get my hand out of the way there. And I'm going to name this particular one ABC. So I've got point A there, B at the vertex, and C. Now we know that this angle has some set measure. In our case, we measure in a number of degrees. Now what this theorem is stating, the measure of the angle, so the measure of angle ABC, is or equals 1/2 of the measure of the intercepted arc. And the measure of the arc, in this case, remember our intercepted arc would be from point A to point C. So the measure of that arc. So the measure of the angle is half of the measure of the arc. All right, the second theorem, if 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. So let's start with an intercepted angle, and I'm going to draw my 2 angles in separate colors so that we can really see this relationship. Okay, so let's start with this angle. And I've just drawn some random angle, it doesn't matter what it is. That angle would correspond to, let's name it PQR. So there's PQR. And according to this theorem that we had up above, the measure of angle PQR is half of the measure of the arc from P to R. Okay, so far we haven't used this theorem at all. We've only used that one, the first one we talked about. All right, so in this case, we need 2 inscribed angles. We have one already. 2 inscribed angles that intercept the same arc. So in this case, we need another angle that intercepts arc PR. And in this case, that particular arc, PR means I've got to have the same endpoints. I don't think I want to use that orange. It's just a little too close to the pink. So I've got to have the same endpoints here, but I don't want to use the same point Q. So let's choose a point down here and we'll call it T. And I'm going to let that be the vertex of my second intercepted angle. Excuse my dog. She doesn't like anybody to walk outside. All right, so we have an intercepted arc, in this case of PR, just as we did before, but with a different angle. In this case, angle PTR intercepts arc PR. So from that intercepted angle, I know that the measure of that inscribed angle PTR is 1/2 of the intercepted arc PR. Let's kind of think what's going on here and why this theorem works. We have two angles, both of which have a measure equal to 1/2 of the measure of arc PR. So if these two quantities are the exact same quantities, then these two angles must have the same measure. They must be congruent. So from the fact that these two statements are true, this theorem says, then it must be true that angle PQR is congruent to angle PTR. So this angle PQR and this angle PTR are going to be congruent to one another because they intersect or intercept the same arc. All right, so that takes care of our two relationships that we need then based on these definitions that we've talked about at the top. The measure of the inscribed angle is 1/2 of the measure of its intercepted arc, and if two angles intercept the same arc, then they have to be congruent to one another. So with that in mind, let's look at some examples. We have example 1 here at the bottom of the page and then a few more examples on the back. So example 1, find the measure of angle ABC. So we can see that angle ABC is an inscribed angle, has its vertex on the circle, and the sides of the angle are chords. So according to the theorem, the measure of the angle ABC is equal to 1/2 times the measure of the arc that it intercepts. So if I start at A, stay inside that angle, and go to C, the other endpoint, then this makes an angle of 212 degrees. So the measure of angle ABC will have to be 1/2 of 212 degrees. So 1/2 of 212 is 106 degrees for the measure of angle ABC. And that takes care of our first example. Now let's look at some other examples back here on the back of the page. So in this case, we have several angles going on here. Let's see what's going on here. Find the measure of angle QJP. So let me see, QJP would be here. And I can see that it intercepts this angle or this arc that's 88 degrees. So the measure of angle QJP is going to be 1/2 of that intercepted arc. So the measure of angle QJP is 1/2 of the intercepted arc, 88 degrees. So in this case, 44 degrees is the measure of that angle. Okay, now let's look at the second angle we're asked for. The measure of angle QMP. So QMP, there again, then I can see that it's going to intercept the same arc from Q to P, which means because it intercepts the same arc as the angle QJP that we just talked about, that tells me that the measure of angle QMP must also be 44 degrees. They intercept the same arc, they have to have the same measure. And then as we look at the last one, the measure of angle QNP, here again, as we start to highlight that, we can see that Q and P are the endpoints there, again, of that same intercepted arc. So there again, that angle QNP has a measure of 44 degrees. So all three angles had the same intercepted arc and must therefore have the same measure. All right, number 3. Find the measure of angle CAB. Okay, so something that I noticed right away, segment AB is a diameter, and I know it's a diameter because it's a chord that passes through the center, and I can see the center is marked there. Now, because that's a diameter, it means that each arc on either side of that diameter is going to have to total 180 degrees, which tells me this arc, which has a measure of 8x minus 8 degrees, and this arc from C to A, which has a measure of 6x plus 20 degrees, that those have to total 180 degrees. So with that in mind, let's see what that makes the value of x become. So their sum must be 180 because they form a semicircle. So combining of like terms, and then solve this nice two-step equation. So 14x is going to equal 168, and then we divide both sides by 14 to get 12. All right, now if x is 12, then let's go back and talk about what that means for these arcs. So if x is 12, then 8 times 12 minus 8 is going to give me a measure of, what is that? 8 times 12 minus 8, 88. So this one's 88 degrees. And 6x plus 20. Nice thing about this too is that I can use this to kind of check my work and make sure that these do in fact total 180 degrees. So 72 plus 20 gives us 92. And looking at these two values, they do total 180 degrees, so that's good. Okay, now with that in mind, let's answer the question that we're asked. Find the measure of angle CAB. So CAB has an intercepted arc here of arc BC, which we found to be 88 degrees. So the measure of angle CAB, that inscribed angle, is going to be 1/2 of the intercepted arc, 88. Which there again gives us a value of, or a measure of, 44 degrees for the measure of angle CAB. It was totally unintentional that my angles had the same measure between numbers 1 and 2. All right, last one, number 4. If the measure of angle RSQ is 2x plus 26, so RSQ, 2x plus 26. And the measure of angle RFQ is 4x minus 2, so here's my RFQ. Find the measure of arc RQ. Okay, so I'm trying to determine the measure of this arc here. Now, if I look at the first angle, RSQ, I can see it's an inscribed angle, and its intercepted arc would be that arc RQ that I'm looking for. So if I knew the measure of this angle, I could double it to determine the measure of the arc itself. Now, as I look at the second angle, RFQ, there again, it's an inscribed angle. It has a vertex on the circle, and it has the same intercepted arc. So according to our theorem on the front side of our notes, if two angles have the same intercepted arc, then they have to be congruent to one another, which means in this case that the 2x plus 26 and the 4x minus 2 have to be equal to each other in order for those angles to be congruent. All right, so we solve like we've done many times before with equations and find the value of x. Now, in some problems, finding the value of x will be your final solution. That's all you're asked for. In this case, it's not. All right, in order to find the measure of arc RQ, we need to know either the measure of angle RSQ or the measure of angle RFQ, and those should be the same value. Now, the nice thing you could do in this case, we could check it in both and make sure that we do have congruent angles as we should have. It's not always a bad idea. That can save you from those embarrassing, silly mistakes where we like add wrong or we accidentally type the wrong button into the, press the wrong button on the calculator, etc. So here, I'm substituting into angle RSQ, 2 times 14 plus 26, and I get a value of 54 degrees there. If I substitute into angle RFQ, 4 times x, 4 times 14, minus 2. 4 times 14 is 56, minus 2 is 54. Okay, so that tells me that my value of x is correct, because I did in fact get two congruent angles. All right, so the measure of the angle is half of the measure of the arc. So if I think about it in the terms, in that case, the measure of the angle, 54 degrees, is 1/2 of the measure of the angle, or the arc rather, RQ. Now if I want to get this value by itself, if I want to isolate it, then that means I need to somehow get rid of this 1/2. And there are two ways that you can do that. You could divide both sides by a half, since these are being multiplied, or we could multiply both sides by 2, the reciprocal of 1/2. So if I multiply by 2 here, the 2 and the 1/2 produce a 1. Multiply by 2 on this side, 54 times 2 gives us a measure of 108 degrees for the measure of angle arc RQ. I said angle in there, didn't I? It's the measure of arc RQ. All right, and that takes care of our last example on this set of notes.